Last video we saw that if we find a stress function that satisfies the Poisson's equation and the boundary conditions, then the volume under that stress function is the torque. Let's see if we can use this idea to find the torsional constant of an elliptical V-shaped shaft. The shaft has major and minor axes A and B as shown here, and we would like to find its torsional constant. Can we find a stress function phi of xy that satisfies the Poisson's equation and phi equals 0 on the boundary on the elliptical curve? So let's guess the stress function. We can find one that is 0 at the boundary by simply taking it to be the equation of the ellipse. And then let's multiply it by a k and see if this guess function will satisfy Poisson's equation. So if we substitute it into it, we see that if we pick k equals minus g theta times a squared b squared divided by a squared plus b squared, such a stress function will satisfy Poisson's equation and the boundary conditions. So now that we have a stress function, let's compute the stresses. Sigma xz is d phi by dy, sigma yz is minus d phi by dx. So if we plot the tractions corresponding to this stress, we get shear tractions on the cross section, which makes sense, which is consistent with our notion of what kind of stresses a torque would produce. Next, let's compute the strains. So the strains are simply the shear stresses divided by the shear modulus. And then we can integrate the strains to compute displacements. And we'll use the displacements to calculate what the warping is. So we know that gamma xz is minus theta y plus dw by dx. So if we move things to the other side, we get an expression for dw by dx. Similarly, we get an expression for dw by dy starting from gamma yz. So integrating the first equation, dw by dx, gives w of xy equals theta times x times y times b squared minus a squared divided by a squared plus b squared, plus some arbitrary function of y, like an integration constant. If we then differentiate with respect to y and compare with the expression for dw by dy, we get that f prime of y is equal to 0. And since only the derivatives of w matter, we can take f is equal to 0 as well. So we see that the warping function w of xy is b squared minus a squared divided by a squared plus b squared times theta times x times y. Let's see what this function, and notice that for a circle a is equal to b, so the warping function is 0 as expected. Let's see what this warping function looks like by plotting contours. And we see what the contours look like. And in the first quadrant, points are, the surface is coming out, so it warps out. In the second quadrant, it warps in. In the third quadrant, it warps out, and so on. Now let's calculate what the volume under the stress function phi is. So we do twice the integral over the area of phi of xy dx dy. Substituting x equals ar cosine alpha for some alpha, y equals br sine alpha, and just doing the integration, we find that the torque is g times j times theta, and from that we deduce that the torsional constant is pi a cubed b cubed divided by a squared plus b squared. And if we substitute a equals b, we get pi times a to the power of 4 divided by 2, which is the torsional constant of a circular shaft.